Hello, my name is Jim James, and today I'm going to be talking about my RIS 2023 project, Dense Depth Completion for Programmable Light Curtains. Before getting into the specifics of the project, I'd like to briefly discuss the importance of accurate depth data. Accurate depth can be used for guaranteeing safety in various human-robot interaction tasks, such as advanced driver assistance systems and autonomous vehicles, factory robotic manufacturing, and medical robotic assistance. However, accurate depth data is actually surprisingly difficult to obtain, as we'll see soon. One of the typical ways of obtaining depth is through LIDAR sensors. However, these sensors, if you want a high resolution or dense one, are actually rather expensive. A typical LIDAR sensor that's high resolution may cost as much as tens of thousands of dollars for a single sensor, which makes it cost prohibitive for typical consumer uses. On the other hand, an alternative approach is monocular depth estimation, which simply relies on an RGB camera, which therefore would provide high resolution and inexpensive depth. However, these results are typically inaccurate because of issues like scale ambiguity. In the following image, you can see how the monocular depth estimation network has distorted many of the elements of the scene, particularly this paper towel dispenser on the wall. On the other hand, we have a new and exciting sensor known as a programmable light curtain developed here at the ILM. And the way that this sensor works is that it uses a line laser as well as a IR camera to scan for depth alongside some ruled surface, which is basically if we took a 2D curve like this S shape here and extrude it vertically, we would be able to find any depth alongside that curve. The advantage of this sensor is that this curve can be user specified, so it's not something that's predefined, meaning that every time we query the sensor, we can get different points. And we can query up to 45 surfaces per second in high resolution, since the resolution is only limited by that of the camera. Because this effectively only relies on a laser and a camera, it's also a fairly low-cost sensor, which alleviates the problem that LIDAR has. So in order to drive this sensor, we need to actually choose these curtains or these ruled surfaces. So a couple of different strategies exist for doing this. One of this is using a planar sweep, where we effectively just sweep a plane across. One of them is that we use handcrafted features, but this requires prior knowledge of the scene, which is difficult. And finally, in our opinion, the best one to use is called random curtains, where we can very quickly sample different points in the scene randomly, which over time will give us a pretty reasonable reconstruction of the scene, as we'll see in this video. Based off this, we propose the use of random curtains with a diffusion model-based inpainting pipeline in order to predict dense depth values of the scene. I'm going to briefly discuss how diffusion models work, since they may not be familiar to everyone. So the way the diffusion model works is that we have a forward process that converts an image to white noise. And basically all this means is that in several steps, we rescale the image and add a little bit of Gaussian noise. So this effectively maps the image space to the standard normal distribution. Then when we want to actually generate an image, what we do is that we step-by-step learn a denoising step through a machine learning model. And since this is an iterative process, we can repeat this multiple times in order to get less noisy outputs, which fits itself very nicely with our light curtain, which is also an iterative device. And since this noise prediction model is pretty arbitrary, we can also take an extra input as conditioning in order to guide this denoising process. So for example, we can take in an RGB image in order to inform the diffusion model about the scene. A lot of recent works for monocular depth estimation have utilized diffusion. One of these is diffusion depth, which we utilize in our work. Basically, diffusion depth uses a Swin transformer alongside RGB conditioning in order to predict depth of the scene in a dense manner. In our case, we modify this slightly by replacing the encoder and decoder with a separately trained variational autoencoder, and then we also supervise it with metric depth, so that way we can guarantee that the depth is on the same scale as that provided by the light curtain. In order to actually utilize this model then with our light curtain points, we actually propose an in-painting pipeline. This allows us to set a hard constraint that the values at the known light curtain points will be reflected in whatever the diffusion model outputs. So this pipeline works by encoding the light curtain points and then adding noise according to whatever the noise schedule says it should be, and then finally masking it off to only reflect the known points from the light curtain. Simultaneously, we do the standard diffusion-based denoising alongside the inverse of the previous mask, and then summing these two things together yields the denoised output for the previous step. So we just repeat this as many times as we need in order to get our depth. One challenge with diffusion models is that they do take quite a while to train, so unfortunately our in-painting model is still untrained. However, in the meantime, we do compare two simple baselines qualitatively. And the first of these is sparse to dense, which is a RGB encoder-decoder network. And we also compare a diffusion depth model fine-tuned on light curtain points in order to try to incorporate that into the prediction. As we can see from these results, sparse to dense does not produce high-resolution outputs. It generally produces very coarse depth maps, which result in a very poor reconstruction of the scene, while the fine-tuned diffusion depth struggles with scale. And if we actually look at the scene reconstruction, again we see this problem similar to monocular depth estimation, where it's distorting scene elements. I'd briefly like to discuss some challenges and limitations of our setup. One of them is that we have significant training issues with the diffusion model, namely because these diffusion models take quite a long time to train. Another issue is that diffusion models are slow, meaning that inference may not necessarily be fast enough for certain mobile applications. For instance, our benchmarks show that it runs at 9.1 FPS on an RTX 4090 and 3.3 FPS on an RTX 3060, meaning that it likely will not be fast enough to run in real time on something like a Jetson Nano or Jetson Xavier, but it likely is still fast enough to be used with a high-end laptop. Our in-painting pipeline also assumes that the light curtain points are still valid between iterations, meaning that it's limited strictly to static scenes, since any motion would break that assumption. Finally, for future work, we would like to make the network also design curtains instead of necessarily using random ones. There are some strategies that may help with this, such as looking alongside edges in the RGB view in order to make sure those are sharp, as well as using the confidence predictions produced by the diffusion model in order to design a specific curtain for the scene. We can also try to extend the existing model to non-static scenes by working in things like velocity estimation from points from both the light curtain and the RGB data. Thank you for listening to my presentation.